Hello there, and welcome back to Sleepy Science Stories. I'm glad you've arrived here in this quiet moment between thoughts. Perhaps you're already lying down your room, dim the edges of the day softening into night. Perhaps there's a window open nearby and cool air drifts slowly across the space between you and the dark. Wherever you are, you don't need to do anything now. No tasks, no expectations, just this calm space to breathe and listen. Above us, the stars move gently, though we never feel their motion. The Milky Way turns galaxies drift, and deep among them, strange stars hum with invisible rhythms. Tonight we'll explore some of the strangest of all neutron stars, tiny remnants of once mighty suns. Objects so dense that a teaspoon of their matter outweighs a mountain, and yet so small they could fit inside a city. They spin, they pulse, they shine, and sometimes they whisper in ways that defy our understanding. Astronomers have watched these remnants for decades: pulsars, magnetars, collapsing stars, turned into cosmic clocks. But even now, the universe continues to surprise us. In recent years, new observations have revealed behaviors so unexpected, so utterly outside what physics predicted, that they seem almost to belong to another category of existence. We'll move through 4 of them tonight, each a small mystery folded within a larger one. We'll meet a star that blinks every 22 minutes, a silent beacon that produces antimatter, a network of pulsars listening to the deep gravitational hum of the cosmos, and flashes of blue light faster and brighter than any known explosion. Before we drift further, I'd love to know, where in the world are you listening from tonight? A city window, a quiet cabin, somewhere under a sky full of stars. It's always a small wonder to imagine this same stillness shared across oceans and continents. And if these calm explorations help you slow your thoughts, a gentle like or a soft tap on subscribe helps other sleepy minds find their way here too, one quiet soul at a time. As we begin, breathe softly. Let the air fall in and out without effort. The world beyond your window is still turning, but here for now, you are still. Let your mind drift outward past the quiet room, past the clouds, into the deep silence between stars. Somewhere in that silence, a single pulse begins, and we will follow it. Somewhere in the southern sky, beyond the reach of ordinary sight, a single point of radio light blinks slowly, not seconds apart, as most pulsars do, but minutes. 21 minutes and 58 seconds each interval, precise, unwavering, and impossibly long. The signal was first noticed in 2022 by the Murchison Wide Field Array, a radio telescope lying in the red desert of Western Australia. Out there, far from city noise, the sky is clean, a dome of silence pierced only by the soft breath of the universe. Among that silence, the array heard something that did not belong to ordinary noise, a pattern, a voice repeating with calm insistence, a pulse every 22 minutes. Not once, not twice, but over and over, each flash lasting less than a minute, then vanishing again into the void. When astronomers traced the signal, they found something stranger still. This source, now called GPM J1839-10, was not new at all. Archival records data, stored and forgotten faint traces from the 1980s, showed the same signal, steady as a heartbeat, unchanged for more than 35 years. That kind of stability is almost impossible. Stars change, magnetic fields decay, spin rates drift. Yet this one remains exact, its rhythm as constant as the rotation of Earth itself. No acceleration, no fading, no sign that it even notices the passage of decades. Scientists recognized at once that it must be compact something small enough to spin in under half an hour and bright enough to beam radio waves across space. That points to only a few possibilities: a neutron star, a magnetar, or perhaps a white dwarf. But each possibility seems to dissolve when examined closely. In the simplest picture, neutron stars behave like cosmic lighthouses. They rotate quickly, sometimes hundreds of times each second, and their magnetic poles sweep beams of radio light through space. If one of those beams crosses Earth, we see a pulse. Steady, rhythmic, a metronome carved into space-time. But for such pulsars, the light depends on motion. The faster the spin, the more energy the star can give to its beams. When rotation slows below a critical threshold, the lighthouse goes dark. Physicists call this silent realm the pulsar death valley, a region in which the electric fields can no longer pull particles from the surface, no longer light the beam. GPM J1839-10 sits deep inside that valley. A rotation period of 22 minutes should be far too slow for any known mechanism of pulsar emission. Its magnetosphere should be cold, its radio beam extinguished long ago, and yet every 22 minutes it shines again. That impossibility keeps astronomers awake. It suggests either that the object disobeys the rules or that the rules are incomplete. Perhaps there exists a regime of neutron star physics we have not yet entered a way for magnetic fields to twist and reconnect, even when rotation seems too slow to feed them. Imagine such a star, a body no larger than a city, its mass greater than the sun's, its surface a lattice of crushed nuclei and degenerate neutrons. Above it, magnetic lines arc like frozen thunderbolts confining plasma that glows faintly in radio light. It spins not fast but stubbornly, carrying that field like a scar around its poles. Every rotation the beam sweeps past Earth again, slow, deliberate, ancient. If this truly is a neutron star, then it sits on the border of what we thought possible, a survivor in the desert of dead pulsars, a quiet monument to endurance. Another thought rises. Perhaps it is not a normal pulsar, but a magnetar, a kind of neutron star wound tight with magnetic fields, 1,000 times stronger than ordinary ones. In magnetars, the crust itself cracks under magnetic stress. Those cracks release flares, sudden bursts of X-rays and gamma rays that flash like lightning in the dark. Such stars can emit even when they rotate slowly. Their power does not come from spin alone, but from magnetic decay, the field eating itself, releasing energy stored since the star's birth. That would explain how GPM J1839-10 still radiates despite its long period. But when astronomers looked for X-rays, they found nothing. No glow, no flare, no sign of the violent heart that defines magnetars. Its spectrum was silent outside radio bands, cool, serene. If it is a magnetar, it is unlike any known before a magnetar that whispers instead of screams. And so that explanation falters too. It fits the shape of the problem, but not the color of its light. There is one more class of compact star to consider: the white dwarf, a remnant less dense than a neutron star, but still the size of a planet, its matter made of degenerate electrons, its spin often slow. Some magnetic white dwarfs can emit radio pulses when magnetic fields accelerate electrons near their poles. Perhaps then this source is not a neutron star at all, but a white dwarf with an extraordinarily strong field. Yet here too, the numbers collapse. To produce the observed radio brightness, the magnetic field would have to be stronger than any white dwarf ever measured, stronger than physics allows their structure to bear. And again, no optical or ultraviolet emission appears to match. Too faint, too cold, too strange. So what remains? A signal that belongs nowhere in the current taxonomy of stars. A rhythm that violates the usual relationships between rotation magnetism and light. An object that has lived unchanging for decades, neither fading nor flaring, as if balanced on a razor's edge between life and extinction. Perhaps then the real answer is that this is something new. Not a neutron star, not a white dwarf, but a hybrid, a body that bridges the two, a missing link in the long evolution of stellar remnants. Some models predict that as neutron stars age, they lose energy and expand slightly their magnetic fields, relaxing. Under the right conditions, their outer layers might crystallize, forming a solid crust that cracks slowly over millennia. Could GPM J18839-10 be such an intermediate object? A neutron star drifting toward a new equilibrium, its magnetosphere half asleep but not entirely silent. If so, the pulses we see could be the final sighs of a dying mechanism, the last embers of a magnetic engine cooling but still capable of light. Or perhaps something more exotic waits beneath the surface, superfluid vortices slipping through nuclear matter, releasing energy in periodic avalanches. Each quake could jolt the magnetic field, briefly reigniting the radio beam. A clock not driven by spin, but by internal rhythm, the star's own heartbeat, slower than any we've known. No single idea fits perfectly, and that imperfection is the beauty of it. The universe offers puzzles not to frustrate, but to remind us that our equations are only sketches of its deeper design. The discovery itself is as poetic as the object. In the Murchison Desert, rows of radio antennas lie across the sand like metallic lilies pointing toward the sky. Each one listens to frequencies that our ears could never perceive, the long, low waves that ripple through interstellar space. When the data from 2022 were processed, the repeating signal stood out as a soft heartbeat in the noise. The astronomers checked for interference satellites, planes, electronics. All were ruled out. The pulse came from the sky itself, from a small region near the constellation Scutum, just above the galactic plane. They named it GPM J1839-10 for its coordinates in that vast map of stars. Nothing visible marked its place. No optical star, no X-ray source, no nebula. Just the patient blinking of radio waves rising and falling every 22 minutes. When they searched the archives, they found it there too in data from 1988, 1991, 1995, each pulse perfectly timed. That consistency stunned them. Even atomic clocks drift over decades, yet this cosmic metronome did not. It was as if the star had been waiting all this time, quietly tapping out its rhythm while we were too busy to notice. What does it mean for a star to keep such calm rhythm in a universe so turbulent? Most pulsars slow down measurably over time, losing rotational energy to their beams. But GPM J1839-10 shows almost no change. That suggests that whatever mechanism drives it must draw on a deep reservoir of energy, perhaps magnetic rather than mechanical. It may also mean the star is old, a survivor from the early epochs of our galaxy, cooled to near stillness, but held together by extraordinary magnetism. Think of it an object only a few tens of kilometers wide, spinning once every 22 minutes, its magnetic field a trillion times stronger than Earth's, its surface gravity so fierce that an atom dropped there would fall 1,000,000 times faster than on our world. And yet, despite those violent conditions, its signal is gentle, a whisper across space, a slow pulse that could lull even physics to sleep. The time between its flashes is longer than the span of a song, longer than a human conversation. In that pause, entire storms pass across our planet, winds rise and fall, people move through their days. Then, once again, from the same patch of sky, a brief flicker, the star reminding us it still turns. It feels almost alive, not because it thinks, but because it endures. It repeats with the patience of stone, with the discipline of tides. When you listen to that rhythm, you can almost imagine the cosmos breathing slowly, evenly in and out for millions of years. No one yet knows what GPM J1839-10 truly is. Telescopes across the world continue to watch it, to measure its pulse shape, its polarization, its drift through the galaxy. The next generation of arrays, the square-kilometer array now under construction in Australia and South Africa, will have sensitivity great enough to catch even fainter whispers from the same source. Perhaps then we will learn whether its beam is changing subtly with time, whether its spectrum hides harmonics, or whether similar stars exist elsewhere waiting to be recognized. If more are found, they could represent a new class of astrophysical object, not pulsar, not magnetar, but something in between. Some have proposed the name ultra-long period magnetar, a term as tentative as it is intriguing. Whatever it proves to be, it expands the boundaries of what we call possible. Every new discovery like this adds another note to the quiet music of the universe, a frequency we had not known to listen for. Imagine yourself lying once more beneath the night sky. The stars above seem still, but now you know that among them one is slowly blinking so slow that you could fall asleep between its pulses. Every 22 minutes, its light travels across thousands of light years, reaches the antennas in the desert, and then, much later, reaches you. Translated into thought, into wonder, into the soft awareness that the universe is stranger and calmer than we ever expected. In this way, GPM J1839-10 becomes more than an astronomical curiosity. It becomes a meditation on time itself, on patience, on rhythm, on the persistence of light. A reminder that even when all seems quiet, something is still turning somewhere faithful to its own slow heartbeat. You can rest here for a moment between pulses, between stars. The pulses fade. The desert sky grows quiet again. But far across the void, another rhythm begins. Faster, sharper, almost musical a flash every quarter of a second, as if a different kind of star were keeping time for the universe. This one is called Geminga, a name that sounds like a whisper, and in Italian dialect, it almost is Geminga, meaning it's not there. A joke born from confusion because for many years no one could find what it was. In the early 1970s, orbiting gamma-ray detectors recorded something peculiar, a bright flickering source of high-energy photons in the constellation Gemini. It shone not in visible light, not in radio, but only in the most energetic form of radiation. No star, no nebula, no counterpart could be seen. Just an empty patch of sky pouring out more gamma rays than anything nearby. Astronomers cataloged it as an unidentified source, and when asked what it was, they could only shrug. "It's not there," one of them joked. But it was a ghost radiating from 800 light-years away, hidden by its own strangeness. For decades, the mystery deepened. Some thought it might be a black hole, others a relic of a supernova long faded. It pulsed in no ordinary way, so no one knew where to look. But in 1991, NASA's Compton Gamma Ray Observatory and its Italian collaborator SAS-2 found what everyone had missed. The gamma rays were flashing rhythmically every 237 seconds. Geminga was a pulsar, a neutron star spinning so fast its beams sliced across Earth 4 times each second. And yet, unlike most pulsars, it was nearly radio silent. No strong radio pulses, no lighthouse beam in the familiar band of frequencies. It was visible only to detectors of gamma and X-rays, as if it existed half in shadow, broadcasting on wavelengths that our atmosphere never hears. Ordinary pulsars live loudly. They fill radio telescopes with chatter, rapid clicks, bursts, storms of electromagnetic wind. Geminga did not. For years, even after its rotation was measured, radio astronomers strained to catch its voice and found nothing. Only in 1997 did a faint murmur appear, tiny radio pulses around 100 megahertz, barely distinguishable from background static. That discovery explained its earlier silence. Geminga's magnetic geometry is tilted so that its radio beams miss Earth almost entirely, skimming our planet with only their faintest edge. Its gamma and X-ray beams, however, shine in a wider cone, and so we see the high-energy light, but almost none of the low. Orientation, not absence. The star was never quiet. We were simply not in the path of its louder voice. Still, the metaphor lingers beautifully. A neutron star that barely speaks, that hides in its own brilliance, that tells its story only through the most energetic light in the universe. A paradox wrapped in magnetism. Geminga lies about 800 light-years from Earth, a modest distance on galactic scales, yet unimaginably far for us. It is the compact remnant of a star that once shone 10 times brighter than our sun. When that star exhausted its fuel, it imploded, crushing its core into a sphere no wider than a city. The shock of that collapse blasted its outer layers away, leaving behind this spinning ember of nuclear matter. Its mass is about 1.5 suns, its diameter about 25 kilometers. Its density defies language. 1 cubic centimeter, a space smaller than a sugar cube, would weigh 100 million tons, and it moves not slowly drifting, but hurtling. Across decades of measurement, astronomers have tracked its motion against the background stars. Geminga races through space at over 200 kilometers per second, a runaway from its own explosion, its momentum a fossil of that violent birth. If you could see it with your eyes, you would not notice the speed. The distance is too vast, the motion too subtle. But the telescopes do see it a gradual drift, a steady flight through the interstellar medium like a glowing seed carried by a cosmic wind. That motion leaves a signature. As Geminga speeds through the thin gas between stars, its magnetic field collides with that gas, compressing it, shocking it, heating it. In X-rays, the result is astonishing. Two long, straight tails streaming from the pulsar like comet trails, each trillions of kilometers long. They extend behind it in parallel, glowing softly in high-energy light, a bow wave of particles plowing through the galaxy. Wherever Geminga travels, it sculpts the medium around it, etching a record of its passage in X-rays and charged particles. This is the Pulsar Wind Nebula, a bubble of magnetic energy where electrons and positrons accelerate almost to the speed of light. For a long time, scientists couldn't see that bubble. Only later, with more sensitive telescopes, did its shape emerge, not symmetrical, not centered, but flowing like ribbons, streaming from a dancer's hand. Here, the story turns stranger still. When cosmic ray detectors aboard the International Space Station, notably AMS-02, the Alpha Magnetic Spectrometer, measured the flux of high-energy positrons, they found too many. Space near Earth contained more antimatter than standard models predicted. For years, this positron excess puzzled physicists. Some whispered of dark matter, perhaps invisible particles, annihilating in space and producing the extra positrons. But when astronomers looked at Geminga, they saw something that might explain it without new physics. Surrounding the pulsar is a vast gamma-ray halo dozens of light-years wide. Those gamma rays are produced when positrons, the antimatter twins of electrons, collide with photons of starlight. By measuring the brightness of the halo, scientists inferred how many positrons escape into space. The answer was staggering. Geminga alone could account for up to 20% of the positrons that reach our detectors on Earth. A single neutron star, small enough to fit within a city, feeding the local interstellar medium with rivers of antimatter. In this sense, Geminga is not just a pulsar. It is an antimatter factory, a celestial engine converting rotational energy into showers of particles that wander through the galaxy for millions of years. Every positron that eventually strikes Earth's atmosphere may be in some quiet way a messenger from this faint star 800 light-years away. Geminga's apparent oddities, its silence, its halo, its tail, all come down to geometry. The beams from a pulsar are narrow, their shape determined by the magnetic field. Depending on how that field is tilted relative to the star's rotation and how Earth happens to be aligned, we may see only fragments of the total emission. If we stood somewhere else in space, Geminga might look perfectly ordinary, a bright radio beacon flashing steadily. But from here its beams sweep past us obliquely so that only the high-energy light crosses our path. It is a lesson the cosmos repeats often, that what we see depends not only on what exists, but on where we stand and how light travels between us and the source. In that way, Geminga teaches humility. It reminds us that silence does not always mean absence. Sometimes a star is speaking. We are merely out of tune. Geminga's light left it 8 centuries ago. When those photons began their journey, human civilization was still carving cathedrals, still mapping coastlines by stars. Now, after traveling through the dust and emptiness of interstellar space, they arrive at our instruments, each photon a fragment of that long journey. Inside the pulsar, the rotation slowly slows. Every turn radiates energy away, each pulse a tiny act of surrender. Over millions of years, it will fade, its beams weakening, its magnetism relaxing. Eventually, it will slip into the quiet realm where GPM J1E3910 already waits, a place beyond ordinary pulsars, beyond emission, where only silence remains. But for now, Geminga still sings its light rippling through space like a steady mantra. What powers this cosmic performance is pure relativity and magnetism intertwined. In the crust of the neutron star, charged particles spiral along magnetic field lines that twist through space at near light speed. Each rotation of the star induces electric fields so strong that they tear electrons and positrons from the surface. These particles accelerate outward, streaming along the magnetic poles, emitting radiation as they curve. That process, called curvature radiation, creates the sharp, regular pulses that define a pulsar's light. In Geminga, the energies are extreme. Gamma-ray photons carry millions of times the energy of visible light. And yet, when they reach Earth, they arrive as gentle detections in the digital stillness of a telescope's sensor. It is humbling. The most violent engines of the cosmos whisper softly by the time their signal finds us. The region around the pulsar is not empty. It's a landscape shaped by the interaction between Geminga's wind and the interstellar medium. There are Schacht's fronts where charged particles collide with slower gas. There are cavities hollowed by radiation pressure. There are boundaries where the magnetic field folds back on itself, reconnecting, releasing bursts of energy like solar flares magnified 1,000-fold. Each of these processes leaves traces in the light we observe. The X-ray tails are longer where the density of gas is lower. The gamma-ray halo glows brighter where positrons are trapped by tangled fields. By modeling those patterns, astronomers learn how particles diffuse through space, a knowledge that reaches far beyond Geminga itself into our understanding of cosmic rays, of how galaxies sustain the delicate balance between creation and destruction. All of this, the pulsar's spin, the positrons, it sends the gamma rays. We measure feeds eventually into our own world. Cosmic rays strike Earth's atmosphere every second, producing showers of secondary particles. Some of those particles ionize air, affect cloud formation, even influence the chemistry of our atmosphere. In subtle ways, the heartbeat of a neutron star, 800 light-years away, touches the weather of our planet. It's a quiet connection, invisible but real. The universe is never truly separate. Every rotation of Geminga sends out energy that long afterward changes the sky we live beneath. Before Geminga's halo was discovered, the excess of positrons detected near Earth seemed to hint at new physics, perhaps the long-sought signature of dark matter. But with Geminga and its neighboring pulsars, the picture shifted. No exotic particles are required. Ordinary astrophysics may suffice. That does not close the mystery. It simply redirects it. Now we ask, how many Gemingas are there? How many quiet pulsars are releasing steady streams of antimatter into the galaxy, their presence hidden by geometry? Each discovery recalibrates our sense of scale. We are surrounded by mechanisms as delicate as clockwork and as violent as explosions, all operating beyond our sight. Geminga is a paradox wrapped in equilibrium. It emits with furious energy, yet presents itself to us as silence. It moves through space at breakneck speed, yet leaves behind structures so graceful they look motionless. It generates antimatter, yet helps us explain the balance of matter. Even its name, "It's not there," feels like a riddle whispered by the cosmos. A reminder that absence and presence are sometimes the same thing viewed from different angles. When you think of Geminga, picture a small dense star drifting through the galaxy with twin trails of blue light. Picture it surrounded by a vast invisible halo of particles that may one day touch the atmosphere above you. Picture it turning 4 times each second for 1,000,000 years more. One day, Geminga will fade. Its rotation will slow, its magnetism will weaken. The twin tails will dissipate, and its gamma-ray song will quiet into the background hum of the cosmos. But even then, its particles will keep traveling positrons, wandering through interstellar space, diffusing into the magnetic fields of the Milky Way. They may survive for millions of years, their energy slowly drained until they meet electrons and vanish in light. That light will be faint and visible to human eyes, but it will join the diffuse glow that fills all space, a whisper of annihilation woven into the fabric of the night. And perhaps in some distant era, another civilization will build instruments fine enough to trace those photons backward and realize that they began near the faint star once called Geminga. GPM J1939-10 taught us about patience, a pulse measured not in seconds, but in minutes. Geminga teaches us about perspective, how orientation and interpretation can turn silence into song. Both are neutron stars, both remnants of death, yet each expresses a different rhythm of existence. If GPM J1939-10 is the slow breath of the cosmos, Geminga is its heartbeat. Faster, brighter, but no less mysterious. And both remind us that in the vastness of space, stillness and motion coexist. As you breathe now, let that idea settle quietly. The universe hums at every scale. Some frequencies we can hear, others wait beyond our perception. Far away, Geminga continues to turn its twin tails, streaming through eternity, while closer to home, scientists prepare new instruments to listen for a deeper sound. Still not light this time, but the trembling of space-time itself. Let your thoughts drift toward that next horizon, where even gravity carries a rhythm and the universe itself begins to sing. Geminga spins on fast and tireless, its beams slicing through the dark. But beyond even its brilliance, beyond the crackle of gamma rays and the quiet of radio pulses, there exists another kind of music, one that does not travel through light at all. It is the hum of space-time itself, a background vibration so slow that no ear could ever hear it, no antenna could ever catch it. And yet, it is there, a deep cosmic chord, resonating through the fabric of the universe. This is what astronomers call the gravitational wave background. And the way we found it was not through telescopes or mirrors, but through a network of stars that already kept perfect time. Every massive object in motion, every planet, every star, every black hole distorts space-time ever so slightly. When two enormous bodies orbit each other, they send ripples outward like stones dropped in a vast invisible pond. These ripples are gravitational waves. When the waves are small and fast, like those from merging black holes the size of suns, They oscillate dozens or hundreds of times per second. Those are the waves we can hear with LIGO, the laser observatory that made headlines in 2015 when it first detected the chirp of two colliding black holes. But the universe is full of larger dances pairs of supermassive black holes, each millions or billions of solar masses circling one another in the hearts of merging galaxies. Their orbits are vast, their motion slow, their rhythm glacial. Such giants send out waves with frequencies 1 billion times lower than LIGO can hear waves that rise and fall only once every few years. To detect those, we need a different kind of instrument, one as big as the galaxy itself. For that, astronomers turned to pulsars, especially those called millisecond pulsars. These are neutron stars spinning hundreds of times per second, their beams of radio light flashing with exquisite precision. Each pulse arrives like the tick of an atomic clock, predictable to within microseconds over spans of decades. If a gravitational wave passes between a pulsar and Earth, it stretches and compresses the fabric of space-time along that path. The distance the pulse must travel shifts ever so slightly, not enough to see, but enough to make the pulse arrive a few billionths of a second early or late. By watching many pulsars at once, we can look for a pattern in those tiny delays. If the pattern matches what theory predicts, it means a gravitational wave or many overlapping waves is passing through us all. This is the work of NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, a patient network of astronomers and radio telescopes spread across continents, listening to the cosmos with unhurried devotion. For 15 years, they observed dozens of millisecond pulsars, 68 in total, using instruments like the Green Bank Telescope in West Virginia and the late Arecibo dish in Puerto Rico. Every observation was a conversation with the stars. Each pulse arrival was measured, logged, compared, calibrated against atomic clocks on Earth. Most of the time, the pulses kept perfect rhythm. But when the team looked closer, they found a faint collective sway, a subtle shared fluctuation linking pulsars thousands of light years apart. That shared motion was the fingerprint of the gravitational wave background. To imagine what they found, picture the galaxy as a giant pond. Each pulsar is a floating leaf. When a ripple passes through the water, the leaves move not randomly, but in a pattern, some closer together, some drifting apart, all responding to the same unseen wave. In 2023, NanoGrav announced the first strong evidence of this slow, all-pervading ripple. Not a single distinct source like LIGO's short bursts, but a steady hum, the blended music of countless supermassive black hole binaries pulsing together across the universe. Each pair of orbiting black holes adds its own faint tone to the chorus. Together, they form a gravitational symphony so deep and slow that its full measure may take millennia to complete. We are hearing for the first time the background noise of creation. The proof lies in geometry. When a gravitational wave passes, it doesn't affect all pulsars equally. Depending on the angle between two pulsars in the sky, their timing shifts are correlated in a specific way, a graceful mathematical curve known as the Hellings-Downs correlation. For decades, this correlation was theory, a promise waiting to be fulfilled. Now, for the first time, NanoGrav's data trace that same pattern. Not perfectly yet, but unmistakably. The odds of it arising from random noise are less than 1 in 1,000. It's as if the universe has begun to sing in harmony, and we are finally learning to hear the tune. To hear such low frequencies, Nanograv uses time as its telescope. Where LIGO's mirrors measure oscillations lasting a few milliseconds, Nanograv's pulsars measure cycles that unfold over decades. The instrument's baseline is not kilometers, but light years, its duration, not seconds, but generations. The experiment's sensitivity improves the longer it listens. Each year adds another measure of the symphony, another fragment of coherence. The astronomers know they may never hear the full song in their lifetimes, but they continue anyway, passing the data forward like a chant that will one day resolve into clarity. The hum Nanograv detected almost certainly comes from supermassive black hole pairs in merging galaxies. When two galaxies collide, their central black holes fall toward each other, locked in an orbital embrace. They circle for millions of years, sending out gravitational waves that ripple through space. Those waves overlap, combining into the low, steady background we now detect. Each tone marks a galactic encounter, a record of cosmic growth. By studying the frequency and strength of the hum, astronomers can learn how often galaxies merge, how massive their central black holes are, how quickly they spiral together. It is not just a detection. It is a new form of cosmic archaeology. Light can be blocked, scattered, absorbed by dust and gas. Gravitational waves cannot. They travel through matter untouched, carrying information from regions no telescope could ever see, the hidden hearts of galaxies, the first instance after the Big Bang. That means this new hum is more than an astronomical discovery. It's a new sense, a way of feeling the universe through the trembling of space itself. For the first time, we have both eyes open, one tuned to light, one to gravity, where light shows us the surfaces of things. Gravitational waves show us their movements, their mass, their dance through space-time. The story of Nanograv is also a story of patience. There is no sudden burst, no headline moment. Only data collected carefully, one pulse at a time. Each observation adds a whisper. Each whisper builds the signal. To detect the hum, astronomers must model every source of noise, the interstellar medium, Earth's motion, even the spin irregularities of the pulsars themselves. It is like trying to hear the tide while standing inside a storm. And yet, with enough time, the storm averages away and the rhythm of the deep ocean emerges. In that way, Nanograv's work resembles the act of meditation. Stillness, repetition, attention to minute detail. An entire field of science built on the discipline of listening. Nanograv is not alone. Similar collaborations exist across the globe. The European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and observatories in India and China. Together they form the International Pulsar Timing Array, a worldwide effort to turn the galaxy into a detector. Each pulsar adds a note to the chord. Each region of sky fills in the harmony. As the datasets merge, the clarity will grow, and the hum will resolve into distinct sources, individual black hole binaries rising and falling, like instruments in an orchestra. Someday, we may even detect the gravitational wave echoes of cosmic events long before galaxies formed, relic waves from the universe's birth still reverberating across time. That would be the faintest music of all the first verse in the Song of Existence. When we talk about these waves, we speak in timescales that stretch human comprehension. A single oscillation may last 10 years. A full orbit of one black hole pair may take millions. Compared to that, our lives are brief sparks. And yet, by aligning decades of data, we can perceive these colossal rhythms. It is as though we stand at the edge of an ocean so vast that even its smallest wave spans centuries. Each gravitational wave marks the turning of cosmic machinery that will continue long after we are gone. We listen for a few years, but the song itself has been playing for billions. Some researchers wonder whether the hum nanograv hears might include more than black holes. It could carry relic vibrations from the earliest moments after the Big Bang, when space itself expanded faster than light in a brief incandescent surge called inflation. During that time, tiny quantum fluctuations were stretched to cosmic scales, leaving ripples in space-time that still echo today. If those ripples contribute to the background hum, we would be hearing the fossil sound of the universe being born. Imagine that the low-frequency memory of creation still passing through us, through the earth, through the atoms in your body with each silent oscillation. We exist inside that music, made from it, listening back toward our own beginning. There's something quietly human about the way nanograv works. The researchers spend decades measuring differences of billionths of a second. They fight for funding repair telescopes damaged by storms, train new generations to inherit the data. They will never touch what they study, never see it directly. Their evidence is written in timing residuals and statistical curves, and yet what they have found is nothing less than the trembling of reality itself. Science often feels distant, but this kind of work is intimate in its patience. To listen for so long is to practice faith, faith that the universe speaks, and that silence is never truly empty. Think back to Geminga. Its positrons reach us after centuries faint particles carrying a record of its spin. Now consider the pulsars of nanograv. Their beams, equally precise, carry not only their own stories, but the imprints of gravitational waves passing through. Both are messengers. Both transform the cosmos into a medium for timing. In Geminga, we see matter and energy. In nanograv, we see structure and rhythm. One speaks in light, the other in vibration, and both describe a universe woven from pattern and patience. If you could translate the gravitational hum into sound, it would not be a melody in any human sense. It would be an ever-shifting bass tone so low that its period might last longer than civilization itself. A sound that is also a silence. Everywhere, always, space stretches and relaxes by a fraction of the width of an atom. Our bodies move with it. Our planet breathes with it unaware. And yet, once you know it's there, the thought reshapes everything. Stillness is not still. Silence is not silent. Even in the vast calm between galaxies, the universe hums softly to itself. For decades, astronomers looked outward chasing light. Now they are learning to listen inward to the gentle shaking of the stage itself. The discovery of the gravitational wave background is not an ending, but an overture. From here, each refinement in the data will reveal new harmonics, new structures hidden in the deep base of creation. One day, we may isolate individual black hole pairs, measure their orbits, trace the evolution of galaxies through the slow pulse of gravity. But tonight, we can rest simply in the knowing the universe is not silent. Its quietest moments still vibrate. Its emptiness is full of song. Breathe. Let the hum sink into the rhythm of your own pulse. Light flickers, space trembles, and yet everything holds. The universe hums quietly, its fabric rippling with long, slow waves. And yet scattered across that steady sea, there are moments of sudden fire. Moments when the darkness flares, burns blue, and fades before you can even name it. They are called LFF. Luminous fast, blue optical transients. A name as clinical as it is mysterious. Fast because they rise and vanish in days. Blue because their light is hot electric, the color of the most energetic stars. Luminous because they outshine everything near them, 100 times brighter than a supernova and yet 100 times shorter lived. To encounter one is to witness a heartbeat of the cosmos, an explosion that happens too quickly for comprehension, too powerfully for reason. It began in June 2018. In a small galaxy about 200 million light-years away, a telescope in Hawaii called Atlas caught sight of a new object. It appeared suddenly, a bright, pale blue spark in a spiral arm of the galaxy CGCG 137068. At first, astronomers thought it was a supernova. Stars die all the time. Their last breaths light up the night. But this one behaved differently. Its brightness climbed not over weeks, but in a single day. It glowed fiercely, then began to fade just as fast. They named it AT20AT Cow, from the automated naming sequence Cow by coincidence. But the coincidence felt apt. The universe had given them a creature unlike any seen before. Bright, baffling, radiating blue light that defied every model. Its spectrum showed no heavy elements like those produced in typical supernovae. Its temperature was tens of thousands of degrees, and in X-rays it pulsed erratically, as though something deep inside was still alive. After the cow, others followed. The koala, the camel, the Tasmanian devil, the finch. Each discovered by different observatories, each flaring with impossible speed and color. The names became playful, but the phenomenon was anything but. The pattern grew clearer, each event rose within a day shone intensely blue for only a short time, then decayed faster than any known explosion. Most appeared in the spiral arms of galaxies' regions rich with young stars and gas, the birthplaces of supernovae. But their energy, their symmetry, their brief violent glow did not match the signature of a collapsing massive star. Whatever these were, they were something new. In ordinary supernovae, light takes time to escape. After the core collapses, shock waves must travel through the star's outer layers, heating and scattering them. It can take weeks for that energy to diffuse, and longer still for the light to fade. But LFB-aughts rise in hours. Their brightness peaks before a supernova would even begin to shine. It's as if the energy has no layers to climb through, no envelope to slow it. The explosion is naked, direct, a bare engine exposed to space. Such speed demands an extraordinary mechanism, one that channels power instantly without the delay of diffusion. Perhaps a compact object, a neutron star, or a black hole, sits at the heart of each flash, converting gravitational energy into radiation with ruthless efficiency. If so, LFBOTs might be cosmic laboratories for the moments after death, where the remains of stars still struggle to define what they have become. In 2022, one LFBOT broke even its own rules. Astronomers called it the Tasmanian Devil for its wild, unpredictable bursts. Unlike others that faded quickly, this one brightened again and again, 14 separate times, each flare as luminous as the first. Telescopes across the world tracked it obsessively. No supernova behaves this way. No known explosion reignites itself so often. It was as though the engine inside was spinning up and releasing energy in waves, a pulsar or magnetar born in the heart of chaos, still adjusting to existence. Its light came from somewhere compact, no larger than our solar system, but its energy equaled billions of suns. Each flash brief as it was pushed against the edges of known physics. Then came the Finch in 2023, a flash in the dark space between galaxies 3 billion light-years away. That one changed everything. Until then, all LFBOTs had occurred in the arms of spiral galaxies where massive stars die. But the Finch appeared in isolation between galactic systems in a region where few stars should exist at all. If it was not a dying star, what could it be? Some proposed that the Finch was the result of a star being torn apart by an intermediate mass black hole, a rare kind of black hole 100 to 1,000 times the mass of the Sun. Such events could release enormous bursts of energy as the star's material spiraled inward and vanished. Others suspected a merger of neutron stars, a kilonova without the gamma-ray burst. But LIGO, the Gravitational Wave Observatory, was offline at the time. No vibration reached Earth to confirm it. So the Finch remains an orphan, a flare in the wilderness, a light without a clear source. Each new LF-bot blurs the line between categories once thought firm. Are they collapsing stars or accretion events or something entirely new? The magnetar model suggests that some supernovae leave behind neutron stars, so strongly magnetized that their fields spin up the debris, heating it into a luminous blue flare. That could explain the fast rise and erratic X-rays. But not all LF-bots fit this model. Some show no sign of magnetic afterglow. The tidal disruption model, where a black hole tears apart a passing star, explains the Finch's isolation. But those events usually last longer, their light redder. Each explanation works for some and fails for others. The truth may be that LF-BIOT is not a single phenomenon at all, but a family of rare energetic processes that happen across the spectrum of stellar death. Each one a flare of transformation. Each one a reminder that the universe doesn't repeat itself, it improvises. The blue in their name is not poetic accident. It is the signature of heat temperatures above 20,000 degrees light, peaking in the short electric wavelengths. That color is the hue of violence. It is the color of newborn stars, of fusion's first breath of plasma stripped bare of atoms. To burn that blue is to stand at the edge of destruction. Yet in the calm of night, when you hear about such things, blue feels cool, serene. We forget that in astrophysics, blue means intensity, the short, fierce heartbeat of the universe. The paradox is fitting. Every LF-BIOT is both fury and calm, a burst of incomprehensible energy, yet also a mathematical grace obeying rules we are still learning to write. Unlike supernovae, which spread evenly like spheres of fire, LF-BOTs are highly aspherical. Their light curves suggest that their explosions are directional jets of energy piercing through matter rather than expanding smoothly outward. This asymmetry could explain their speed and brightness. When we look straight down a jet, we see the full glare of its emission. Seen from the side, it might have looked ordinary, perhaps even invisible. So, the apparent rarity of LFBOTs may be an illusion of perspective, a handful of lucky alignments in which we happen to stand in the path of their beams. In that way, they mirror Geminga, another reminder that orientation shapes perception, and that what we call rare may only be what we happen to see. To catch something so brief, astronomers need instruments that never sleep. Surveys like ATLAS, Zwicky Transient Facility, and soon the Vera C. Rubin Observatory in Chile watch the entire sky night after night, comparing images in real time. When a new point of light appears, software flags it, instantly alerting telescopes across the globe. Within minutes, they swing toward the source optical infrared X-ray radio, a symphony of observation. It's a race against time. By the second night, the flare may already be fading. By the third, it might be gone. And yet from those brief windows, astronomers build models, infer masses, temperatures, mechanisms. Each LFBOT becomes a chapter in the fast-moving book of cosmic change. Now the James Webb Space Telescope joins the search. Its infrared eyes can peer into the cooling embers of past LFBOTs, seeking faint host clusters or lingering dust. If the Finch truly came from an intermediate mass black hole, Webb might spot a hidden globular cluster nearby, the kind of dense stellar nest where such black holes might live. If it finds nothing, the mystery deepens. Perhaps the Finch was born in a rogue star adrift in intergalactic space, a wanderer caught and torn apart by a dark companion we cannot yet see. Each new observation pushes the question further until even the act of asking feels like staring into lightning. Unlike the steady hum of nanograv LFBOTs, have no rhythm. They are not periodic, but singular one-time events, each a brief conversation between gravity and energy. And yet, both reveal different aspects of the same universe. Nanograv teaches us patience to hear what lasts. LFBOTs teach us wonder to see what doesn't. One stretches across decades. The other vanishes in a night. But both speak of transformation matter into light motion, into vibration, silence into meaning. Even the hum of space-time and the flash of a dying star are not opposites. They are ends of the same spectrum, each showing how the universe moves between stillness and fire. To study LFBOTs is to study impermanence. They flare, fade, and leave no trace. No nebula, no remnant shell. Just a record in our data light curves, plotted spectra archived. It feels almost human, a brief appearance, an intense moment of expression, and then silence. We often imagine the universe as timeless, unchanging, but LFBOTs remind us that it lives in instants too. Creation and disappearance are constant companions. Somewhere right now, another such flash may be happening in a galaxy whose light will reach us long after we're gone. By the time we see it, the event itself will be ancient, its fire long extinguished. And yet, we will still feel its warmth in the data in the act of understanding. From the slow pulse of GPM J11839 to 10, to the humming chords of nanograv, from the antimatter wind of Geminga to these fleeting blue flares, the universe spans every rhythm imaginable, slowest to fastest, coldest to hottest, longest to briefest. Each phenomenon is a different tempo in the great symphony of being, and each teaches us something about ourselves, our capacity to notice, to listen, to wonder. We exist midway between those extremes, longer lived than an LF Biot, shorter lived than a galaxy. We are the pause between pulses, the quiet listener in a restless cosmos. The LFBOTs remind us that discovery is not always patient. Sometimes it flashes once and you must be ready. They are the lightning in the universe's long thunderstorm, illuminating what would otherwise stay hidden. Each one may be the death cry of a star, the birth scream of a black hole, or something stranger, a process we do not yet have words for. But in that brief light, for those few hours of radiance, the universe shows its energy laid bare. No filter, no veil, just pure transformation. As we move now toward the end of this journey, carry with you both the hum and the flash, the infinite patience of gravity and the instant brilliance of blue light. Both are true. Both are beautiful. Both in their own way are the sound of the universe breathing. The blue flash fades, the hum subsides, and the sky returns to silence. For a long while there is only darkness, not empty, but full in its own quiet way. Everywhere the afterglow of what has been lingers like a breath. You have traveled far tonight, through signals that repeat for decades, through stars that drift unseen, through the slow trembling of space and the sudden fire of light. Each one a rhythm the universe keeps without needing to be heard. Now all of it softens the pulses, the flashes, the hum, dissolving back into the still ocean of night. Somewhere a neutron star is still turning. Somewhere gravity still murmurs beneath the noise of galaxies. But you are here in the small gravity of your own breath, where each inhale is a new beginning and each exhale a gentle return to calm. Even the universe rests. Even the stars drift slowly toward silence. There is no hurry in their motion, no fear in their fading. Only the quiet continuity of being endless, patient, beautiful in its change. Let yourself join that rhythm. The rhythm that asks for nothing. The rhythm that simply is. The night holds you now. Its darkness is kind, its vastness forgiving. Somewhere beyond your walls, the same atoms that once burned in stars cool in the air you breathe. They hum faintly within you, ancient and unafraid. You are part of that stillness, not separate from the stars, but made of the same story, the same light slowed to rest. And as you drift now, let thought dissolve into distance. Let the universe continue without you for a while. It knows how. It always has. Sleep the way galaxies sleep, slowly, silently spinning in the dark. The hum carries on. The stars turn quietly. The night remains, and all is calm.